So we're very happy that Wang took her time for this. Wang is a researcher at the University of Ghent, and she will be talking about the sorting model. So there is a modeling that she has been applied to the PLA sorting and with a cost-benefit analysis. So I think this is very interesting for all of you that are working with PLA. And there is a publication that is in preparation. It has been reviewed. Second cycle of review is finalized. So it should be available soon, and we will also add it to the resources that you will receive if this comes out in time. Otherwise, we will notify you later. And more resources have been also shared by Wang, so we will build a sort of list of useful resources for you to go through the material. The presentation, as I said, will be shared. The recording will be made available. It's only we cut out the Q&A. Now, bear with me. I'll stop sharing here. And I will give the chance to Wang to introduce briefly herself, and then you got the floor, Wang. So if you would like to share now, just go ahead, and I will stay with you until I see everything in place with the presentation. Yes, excellent.
Okay. Yeah.
You got the floor. Thank you, Wang. Welcome.
Okay, thanks, Kira, for the kind introduction, and also thanks for the invite. My name is Wang, a postdoctoral researcher at Ghent University, working with Stephen, and I mainly worked on the sustainable plastic waste management, specifically working on the development model for bioplastic and also for sorting and recycling, sometimes also with the EPR schemes. So today it's a pleasure to present here our recent work on cost-benefits analysis of bioplastic sorting. The work presented today is part of PROSPER project, which is funded by the CBE JU. And to give a general idea about our project, as you see here, that our project is a multi-actor project involving the waste management companies like Suez and also the bioplastic producers, Futero, Novamont, and Biotech, and also together with a large sorting test center, NTCP, also large brand owners, experts from policy and also consultants, and also bioplastic producers. And the whole project is trying to demonstrate a technical feasible and financial affordable bioplastic sorting and recycling infrastructure. As you could see the right figure here, the project covers the entire chain of waste management from collection, sorting to recycling, and aiming to proving and minimizing the associated cost and to calculate a realistic EPR cost for bioplastic specifically. And the project has been started 1.5 years ago, so we have achieved several profound outcomes, especially the large scale bioplastic sorting trial conducted at NTCP. So for those interested, you can follow us via LinkedIn or scan the QR code to follow our update and also the further results via our website. Now let's dive into the core. So today I will mainly focusing on the modeling and also economical insights related to PLA sorting within the material recovery facilities. And bioplastic, as we all know, that they has been discussed for a while as a sustainable substitute to fossil-based plastic. They're either green in their origin, being produced from biomass, or green in their end of life, which they can degrade and also which can alleviate the plastic pollution potential issues. And however, with this biodegradable bio-based plastics, they are not like the drop-in bioplastic. For example, the bio-PE or bio-PET, which can be recycled with their fossil-based compartments. The biodegradable bio-based plastics, they have concerned as contaminated by the recycler because the material incompatibility, they can destroy the quality of the recycled materials. And the second concern is because the bioplastic market currently is still below 1%. So which is from a pure economical perspective is the market volume is too little to justify the investment in sorting and recycling. However, there's a limited evidence to support these concerns. Initiated by these gaps, we chose a clear starting point to focus on the PLA first, which is the dominant bioplastic in the current market. So let's go through a detail. What did we do to answer the question, does PLA contaminate other plastic recycling streams? The first is we developed a data framework designed to simulate the PLA packaging waste within a defined material recovery facility, which we also call MRF. And as you see, the left bottom figure here show you the structure of our model. You can see that our model includes three main input, which is the waste composition, separation efficiency, and plant configuration. I will elaborate into a bit more details in the following slides. What the model can provide. So the model provide not only allow us to track where the material goes, also give information related about how much of the materials can be recycled and also the quality of the recovered streams. This allows the waste manager and the recycler to track that the sorting performance at the process level and pinpoint the hotspot for material loss. And also regarding the economical feasibility of sorting PLA, we also coupled a cost-benefit analysis to tackle the question, does it economical feasible to sort PLA? If so, at what scale? Now let's dive a bit more into details about the models. So the first, this is a generalized sorting layout, which you can find in many Western European countries, where the plastic packaging waste are separately collected. As you see that the collected waste is all mixed, including different plastic types and also sometimes with beverage cartons and also with aluminum cans. So all the waste will be loaded on the conveyor belt, and then they will be screened by the drum screen, depends on the material sizes. Afterwards, the air classifier will separate the material by their density into light fractions, for example, the plastic bags, films, and also heavy fractions like the metals and the bottles, etc. Afterwards, the magnetic belt will be applied to recover the ferrous metals, and following by the near cartons to recover the drinking cartons, eddy current to recover the ferrous metals bale. And then ballistic separator will separate based on the material shape into 2D fractions and 3D fractions. Afterwards, a series of near sorters, as you see, will be separate the plastics into dedicated bale based on the polymer types. So in the business as usual scenario will represent the current sorting practice. There's no dedicated near for PLA. So we're assuming in another scenarios analysis with the expansion of PLA, there will be a near dedicated to sort PLA out, and we consider we're assuming to put it in the end based on the logic to sort the larger amount of plastic waste first. Now is the second main input for the model is the waste composition. So we estimated the waste composition of different packagings within the MRF input based on the amount of packaging placed on the market, and also the waste characterization data from the previous work. And also, since we didn't find any public available data regarding the bioplastic or PLA specifically percentage at the current mixed packaging waste. So we estimated based on the fraction of the PLA production within the global plastic production, assuming that there's the same waste generation and also collection rate for both bioplastics and conventional plastics. Accordingly, we calculated that for 2023, there are around 0.12% of PLA packaging waste expected occurs at the MRF input, and it will be growing into 0.41% by 2028 if we take the most optimistic annual growth rate based on the European plastic for PLA productions. Okay, so now let's move to the last main sorting input parameters. It's the sorting efficiency. Benefit from the work done from our group and also close collaboration with the SUEZ and also Test Center and TCP. So we have a well-established database of sorting efficiencies for more than 200 products, including details, products, parts, dimensions, and polymer types. And you can find more details in the reference here. And for the near PLA, we find from the literature, actually, there's several lab scale studies has been reported that there's relatively quite high above 99% of sorting efficiency of near PLA. However, we consider that in real case, when there's a real mixed and also with the contamination on the surface, so we choose a moderate sorting efficiency, which is reported in the CE Delft report, which is also based on the sorting trial conducted by NTCP. So this is 88 is the value we assume in our model for that near PLA sorting efficiencies. And for the PLA we put in the model, we select 21 market available packagings, including different dimensions, different shapes, from bottles to cups to lids, and also to different colors, including also the black items. And for the sorting efficiency, like the drum screens, wind shifter, we were based on the material properties, and for others, it's mainly based on the experiment data from the CE Delft report, and also expert judgment from the waste management companies, and also experts from sorting. Now it's all about how the model structured. Now let's take a look about how the model, what kind of results the model can provide. As I highlighted before, that the model can allow us to track the sorting performance at process level. So here is an example you can see for PLA milk bottles or single-use trials and PLA fumes. We could really to see or visualize how efficient for certain units can separate the target materials. And we can also assess how much of the materials will be end in different bales to assess the bale quality and also potential contamination. Okay, now let's move to the results part. The Sankey diagram here show you how the material flow of different PLA packaging within the business as usual scenarios where there's no dedicated near for PLA. As you could see that majority of the PLA packagings in terms of all different types of applications, they all ends in the residual, like above 98%. In comparisons, if we implement one near dedicated for sort of PLA, we could see there's a significantly reduced amount in residual, and instead we get a dedicated valuable PLA bale for further processing. And we also find the presence of PLA in the PET bottle bales is very scarce, and this further indicating that it's unlikely the PLA will contaminate the PET recyclings, because as you see, even on the current practice, there's no near for sorting PLA. The presence of PLA within the PET bottles is very, very low. To also to do the scenario to accommodate the future that there's expansion of PLA applications in packagings. So we did a scenario analysis. As you see the figure here, this is the residual amount versus the increasing amount of input PLA at MRF systems. As you see that with increasing input PLA at MRF, the reduced amount in terms of business as usual and plus near scenarios increases significantly. And the reduced residual amount is closely associated with disposable cost, because the residual from the sorting plants normally will be disposed in the landfill or in the incineration for energy recovery. This also associated with the greenhouse gas emissions and also with the environmental impacts. Since we mentioned that the PLA presence at PET bale, under the current situation, which is relatively low, PLA share is very low, but so we're also curious about if there's an increasing amount of input PLA at MRF system, how it works. The figure here is show you the PLA presence in the PET bottle bale, and also along with the increasing input PLA share. The dashed line here is indicating the maximum threshold value of PLA without disturbing the PET recycling. As you see that we are here, which is far below the threshold value. And this is also similar trend was found in the PET trails and also found in other plastic bales. As you see the up table here indicating that even on the high market penetration of PLA, about 20%, the presence of PLA in different conventional plastic bales is still below the threshold values, except the polystyrene bales, because the relatively low input of polystyrene at the MRF. So to conclude that the PLA is not a problematic problem for, and also there's no risk to contaminate other plastic recycling streams. So it's clear that from a technical perspective, there's no problem to sort the PLA, and there's no contamination issue on the current or even future scenarios. However, for a actionable business investment plans, we need figures. So now let's talk about numbers. For the defined sorting systems we just showed, with an annual capacity of 75,000 tons per year, we estimated that the capital investment is around 40 million euro per tons for a quite highly automated systems. And we also estimated the operational cost, and then overall we can get the sorting cost. And we also aware that the conclusion from this assessment is very sensitive towards the cost parameters in the model, because we're aware that all the cost is very country or case specific. For example, the labor cost varies a lot among just even within Europe. And so we also coupled with a sensitivity analysis to accommodate this uncertainty in our cost benefits analysis. So this is the economical part. Now let's go to the results regarding the PLA sortings. The figure here show you the sorting cost of overall plant overall cost, which indicated in yellow, and also in red represent the overall plant sorting cost in business as usual scenario and plus near scenarios. And the star here is indicating the PLA sorting cost. And as you see that on the current low PLA market penetrations, the PLA sorting cost can above 1,200 euros per tons. This is confirms that from a pure economical point that there's no benefits or it's not economical sense to invest in PLA sortings. And we also see that with increasing input PLA, actually there is a sharp decrease of the PLA sorting cost. So this is the pure sorting cost without considering the revenue. If we consider the revenue of saving the disposable saving from reduced residual amount, and if we implementing near PLA, and also with the saving of the sorted PLA, we can find clearly that if the input PLA reach 1% as the defined MARF systems, the net PLA sorting cost is only 170 euro per tons, and the break-even point can be achieved at 2.4%. Afterwards, profitable sorting of PLA can be achieved. Since we mentioned that the conclusion is very sensitive, so we did the sensitivity analysis to identify which factor plays a significant role in terms of the viability of PLA sortings. As you see that the labor cost on the low market penetration conditions, you see the labor cost play a significant role, and the influence decrease along with the increasing input PLA share at the input. This indicating that in countries with low labor cost, actually the required mass to justify PLA sorting is lower. However, on the increasing input PLA amount in the at the MRF systems, we could see the sorted PLA price and also disposable cost of residual play a greater impact on the viability of PLA sortings. And here is a direct overview to show you how the break-even mass was changed in correlation with the change of disposable cost and high market value of sorted PLA here. As you see that disposable cost, we set a range between 30 euro per ton to 50 euro per ton. This is because in some countries, there's more stringent rule for landfill tax and also high gate fee for incinerations. And also for the market value of sorted PLA, we set as 0, which we assume that if there's no market demand for sorted PLA, whereas we assume if there's a high demand with the policy support such as eco-modulations of EPR, and also together with design for recycling guidelines and also more legal requirements, there's going to be increasing market demand for sorted PLA. Then we set a range up to 500 euro per tons. As you see clearly that when there's a high market demand and also more stringent rule for incinerating or landfill valuable bioplastic resources, we could see that actually less of PLA is needed to justify the PLA sorting investment. Whereas if there's a low or no market value for sorted PLA, and also there's a very low disposable cost for the residual, we could see that it's very far away to really achieve, to justify the sorting for bioplastic, especially for PLA. And as I mentioned before, that we chose a moderate sorting efficiency of near for PLA, but from the previous talk, which is by the Antoine from Pelonic, they mentioned that even the partially composted PLA, they can sort it at a efficiency around 95% and achieve a bale quality around 87%. So this indicating that the break-even mass can also associated with the near sorting efficiency. So the figure here clearly show you that the required mass for PLA to justify the PLA investment in sortings is decreased along with the increasing and improvement in near sorting technologies. And also with the development in AI sortings, we believe that in the future that even on the real household waste management sorting plans, with all different mixed waste and residuals, we believe that the high sorting efficiencies can be achieved. Then we expect that earlier break-even point can be achieved even earlier than 2.4% based on our studies. So to sum up, the take-home messages from our work is that the first question is, does PLA contaminate other plastic recycling streams? The first is that PLA is unlikely to disturb PET and all other recyclable streams, even under the current or even future market shares. And also through the economic assessment, we find that 2.4 is the break-even point can be achieved to get for PLA sorting cost equals the benefits. And afterwards, we also find actually with improvement in the sorting efficiency of near, we could really lower the required amount to justify the investment decision for PLA sortings. And in the end, we find that the market demand of sorted PLA and also disposable cost, for example, the gate fee for landfill and incinerations is very have great impact on the viability of PLA sortings. So we expect that if with more legal requirement and also policy support, we believe that PLA sorting can be achieved even at earlier stage. So this is all for the presentation today. And if you have any questions, feel free to approach us by email. And also I'm happy to pick up the questions for now. Thank you.